Real-time reconstruction of fluid flow under unknown disturbance. Our research considers the following reconstruction problem. A solid object is moving underwater. We call this object the agitator. Given the agitator's trajectory, we can simulate its effect on the water flow. But what if the agitator's shape and motion are unknown to us? Instead, we only know the movement of these buoys. These buoys capture the effect of the agitator on the fluid flow. We propose a framework that reconstructs the fluid flow using buoys as inputs. Viscosity parameter optimization. To optimize viscosity parameters, we first need a long pipe. The pipe is densely filled with SPH particles. For easier viewing, the cross-section is shown. If we apply a pressure gradient in the y direction, the liquid flows faster at the center than at the side. This plot shows the theoretical velocity profile for pure water. We want to find the viscosity parameter values that lead to this profile. With an initial guess of the parameter values, we run the simulation. The error of the simulated profile is computed. We then increase each parameter value and repeat the simulation. The errors for these new simulations are also computed. The gradient of the error can then be approximated. Based on the gradient, we update the parameters iteratively. The simulated profile can gradually approach the theoretical profile. With the viscosity parameters optimized, we can proceed to generate training data. Training dataset for reinforcement learning. 15 flow sequences are generated for training. The velocity fields serve as the ground truth. From the 10th second, the agitation pattern changes so that more flow variations can be learned. Validation using synthetic data. The instantaneous velocity score and the height field score are shown in the graph. The scores drop when the agitator's direction changes, but soon rise again as the DNN applies suitable guiding forces. For some agitation patterns, the change in height field is insignificant for evaluation, so only the velocity score is evaluated. Reconstruction becomes more challenging when there are small vortices. Actions of the policy network. Our DNN converts each buoy into a guiding force, which pushes the liquid into motion. The guiding forces work in concert to reconstruct the original flow. The DNN adapts to different numbers of buoys. For fewer buoys, the forces are more sporadic. For 100 buoys, the DNN produces forces for only some of the buoys to avoid excessive guiding forces. With enough training, the DNN also adapts to different agitation patterns. Validation using empirical data. The real-world performance was evaluated using PIV. The variation of the score is comparable to the synthetic scenario. We We also tested the reconstruction performance with freehand motion. For more details, please refer to our paper and our GitHub repository.